Welcome back. This should be a fairly quick video. I wanted to make a video that talks briefly about the physics of transistors, and then a separate video for the operation, and then a separate video where we start to look at the circuit analysis and applications. So if we consider from the Intro to EE course, we know that we had 3 terminal devices called transistors, and a transistor is another semiconductor. And for this case, we're going to look at something called the bipolar junction transistor, or the BJT. Now there's 2 different types of BJTs we can look at. That's going to be the NPN and the PNP. You might ask, what do these even mean? Well, it refers to the semiconductor makeup of the transistor. So if we have an NPN material right here, we have an N-type material, a P-type material, and then another N-type material. Now an N-type material is a semiconductor material that's doped such that it has an excess of electrons, and a P-type has an excess of holes, which is a very odd concept if this is the first time you've heard of this. But nevertheless, then we have another N-type, and it makes up this sandwich. Now the PNP transistor has a P-type, an N-type, and a P-type, and that is the makeup of it. Now why are these P-type and N-type materials even important? Well, if we refer back to our common diode, we can actually represent that as a PN sandwich. So if we had our anode and our cathode right here for our diode, we can represent that with the anode again, the cathode, and then we have this PN junction. And that's going to make the diode. And this is where all that magic happens. So if we can represent a diode as a PN junction, can we represent a transistor in terms of diodes? Now if we consider our NPN transistor here, we know from that earlier video in the Intro to EE course, we had a base denoted by B, collector C, and an emitter E. And if we fit that into our NPN material type, but if we try to connect that with our PN junctions for diodes, this is what we get. So is it safe to say that this transistor acts the same as this, which is kind of like a double bypass valve per se, in an odd way? Well, no. No, it's not. Not exactly. And the short reasoning for this is semiconductor physics isn't that simple. Not at all. It's much more difficult. Now, what we want to do is recall the basic operation of a BJT. So on the left, we have our NPN. On the right, we have our PNP. So we know that if we feed some current into the base, and that goes to the emitter, it kind of opens up this floodgate for current to flow from the collector to the emitter. But if we look at the PNP, I think this is the first time we actually look at this. Well, if we have some current that is able to flow from the emitter to the base, it allows, again, this kind of floodgate for current to flow from the emitter to the collector. And these are only under certain conditions. Now, it is possible to make current flow from the emitter to the collector in the NPN, and this is actually called the reverse active mode, where the collector and the emitter switch roles. Now, most BJTs are specifically designed to operate in the kind of conventional way, and they don't even consider this reverse active mode, but it can exist. Now, if we start to define these modes, we're just going to look at the NPN transistor right here, and we're going to define the active mode. Now, the active mode occurs when the collector voltage is greater than the base voltage, and it's greater than the emitter voltage. So from that, we can assign values VBE, VCE, and VCB. So if we do a KVL, so if we kind of start at the emitter, go up, we have VCE, and then we're going to go down VCB, VBE. So we end up with this KVL right here. Now we can have another mode that's going to be called the cutoff mode. And this is essentially when the collector current is cut off. So no current is flowing from collector to emitter. Lastly, we have something called the saturation mode. And this takes place when you can hand-wavingly say that the BJT is maxed out for how much current it can output. Now, all of these modes don't really mean anything unless we understand the basic behavior of the BJT. But we'll get into that in the next video. So now we can pose the question, why even use transistors? And a very quick answer to that is because they are extremely tiny, extremely useful, and extremely cheap to make. They allow for this current-controlled switch, and that can be applicable in things like digital electronics, even analog electronics. And what we can do is consider a linear regulator, and we can say that if the input voltage, Vin, is anywhere from 12 to 48 volts DC. Well, we can set up our linear regulator with all of these components such that we get an output right here, and that's going to be a constant 5-volt output. So no matter what the input voltage is, the output's going to stay the same. And in the digital case, this can be good for things like microcontrollers or anything that really needs a fixed voltage. Now, this was a much shorter video. Like I said, in the next few videos, we're really going to get into the details of circuit analysis with BJTs. If you learn anything useful or new, please like, comment, share the video, subscribe, helps out. Thank you for watching.